Bismillahirrahmanirrahim. First of all, let me introduce myself. I am Dr. Barka Mohammed, University of Mustafa Istanbuli, Mascara, Algeria. I have a pleasure to present my work for the first international conference on sustainable energy and advanced materials. My work entailed study and characterization of a left-hand medium based on unit metamaterial cell of dual epsilon shape for X-band applications of microwave devices. The outline of the presentation is as following. We start with an introduction, then we move to characterization approach. We have description and unit cell of left-hand medium. Then we have simulation results and discussion. We close our presentation with conclusions. Metamaterials are artificial or pseudo-homogeneous composite structure possessing electromagnetic properties not available in nature. In 1869, analysis of such materials was originally made by Russian physicist Victor Veseligo. He had proposed that metamaterials have different properties compared to conventional media. Here we have permittivity, permeability, and refractive index, and geometric properties such as dimensions of resonator in front of the wavelength inside structures. In this work, a characterization of a new type of split ring metamaterial resonator will be presented. Our proposed dual epsilon resonator represents the electromagnetic characteristic of a left-hand medium for a millimeter period. For the characterization approach, the classic split ring metamaterial resonator is a structure proposed for the first time by John Pandry and his research team. Geometrically, the resonator is formed by two split rings, outer and inner. Physically, the resonator can withstand wavelengths that are too short for a few micrometer. The split ring resonators correctly when the function correctly when the magnetic field will be perpendicular to the plane of the two rings. So for the unit cell of left-hand metamaterial, geometric shape chosen, we have chosen dual epsilon shape. Here we have angle theta in order of 120 degree. The period is estimated by P in order of few millimeter. Here we have also electromagnetic magnetic field which is perpendicular to plane of the ring. The dimensions, the chosen dimensions of our resonator are summarized in this table. Here we have, for example, for A, we have 2 millimeter. For E, we have 0.2 millimeter. For the simulation results, after representing our resonator in 3D modular of our simulator, here we have array box to minimize the losses. Here we have also the substrate on FR epoxy, so our resonator is polarized according to x-axis. After simulation, we have the frequency response. Here we have transmission and reflection coefficients. So for the reflection coefficients, here we represent both amplitude and phase of the reflection coefficient. We can note that our dual epsilon resonator has band stop behavior for 2 peaks of resonant frequency. Also here for the transmission coefficient, we have 2 peaks. We have 2 peaks. The first resonant frequency is in order in 10.18 gigahertz. The second is in order of 11.26 gigahertz. For the phase, we can observe that the phase of the transmission coefficient changed its sign. Here we have the sign which is negative, then we have a positive sign. So for the refractive index, we have the following expression. We have the refractive index, which is given as the permittivity and permeability. Also, we have permittivity and permeability, which has real part and imaginary part, as transmission and reflection coefficient as the frequency. So after simulation, we have the variation of the refractive index. Here we can note that the real part of our refractive index is negative along the range of frequency for 5 to 15 gigahertz. Here we have at the resonant frequency, we have the value of the real part of our refractive index is in order of -9.79 for the real part. For the imaginary part, we have only positive values. For example, around the resonant frequency, we have the values M1, which is in order of -0.04 for the imaginary part. So to characterize the lossless in our proposed resonator, we have the figure of merit, which is given as the following expression, as the real and imaginary part of refractive index. Here we can observe that this figure have two peaks at the two resonant frequency, around 10 gigahertz and around 11 gigahertz. We have the two values. The first value is around of 1.96, and the second is in order of 5.36. So for the representation of the absorption of the DL epsilon metamaterial resonator, here we have the expression which given our absorption as transmission and the reflection coefficients. Here we have also two peaks for the absorption, two important peaks. The first absorption is in order of 85.19%, and second is in order of 94.12%. We can compare our results for other shapes. For example, in this table we have two other shapes. For example, for the first shape, which is the triangular shape, here we have only one peak. For the resonance, only one resonance in order of 2.40 gigahertz, for again, which is -35 decibel. So we can note that a characterization of left-hand medium is presented in this work. This left-hand medium or left-hand metamaterial is formed by a unit cell of metamaterial zone for a dual epsilon shape resonator. Our simulation, which aim to obtain the reflection and the transmission coefficient, are carried out for a millimeter period of cell study. So the obtained result for the characterization of our resonator can show a negative refractive index and a maximum absorption located in the same band, which is the X band, and we have also the left-hand media. For the future works, we have the 3 points: how to propose metamaterial resonator of micrometric, the dimensions for different geometric shapes. Then we have the minimization of the lossless, therefore the choice of the best material, which is the substrate. Then we have exploitation of the electromagnetic characteristics of metamaterial resonator for the optimization of microwave devices. Thanks for your attention.